and then it'll turn fuzzy again. No, I think it's okay. I think. Is it? You guys can tell better than I can from here. All right, let's say we're given a vector valued function x of t, y of t. Then, arc length. Length of this path, the length of that curve, is given by the integral from a to b, square root of x prime of t squared plus y prime of t squared dt. Whoa, we've seen this before. This is the arc length for parametric form. And guess what? It's exactly what we need for the arc length of a vector valued function. Okay? It's the same thing. I mentioned the other day we could change vector valued functions into a parametric form. This is the x, this is the y. Substitute it in, and we have the arc length formula for our vector valued function. Bless you. If r of t is three-dimensional, three-space, and this is what we'll do today. We'll do a three-space one. Okay. Then the arc length is what you would expect it to be, and the integral from a to b, x prime of t squared, y prime of t squared, z prime of t squared dt. And we'll do a typical problem. Let's do a helix, which is a typical problem. Let's take r of t, cosine t, sine t, and t. And let's have t go from 0 to 2 pi. We'll make one revolution, one loop of that helix. Now, here's my question to you. Is the arc length of that helix over that interval from 0 to 2 pi greater than, equal to, or less than 2 pi? Nick is here. Good deal, Nick. Okay. Is that greater than, equal to, or less than 2 pi? Janish, what'd you say? Janish said equal to? That's pretty convincing. If Janish says it, and with some confidence too, equal to. Anybody want to disagree with him?
No, I'd be scared.
Nope, never. Greater than!
You got a reason for greater than? Why'd you say equal to 2 pi, Janish?
If we bring the top down, we do the circle itself.
That's right. It would be a circle, and the circumference of that circle is 2 pi.
But going up wouldn't be longer?
Ooh, maybe if you moved it up off the xy plane like a helix would do, wouldn't that make it a longer path? Yes, it would. Yes, it would. So greater than is going to be the answer. No. Well, it was a reasonable thing that you said. He said if you dropped it down to the xy plane, it does describe the circumference of a unit circle whose circumference is 2 pi. But if you lift it off the xy plane, you're making the path longer, and it should be somewhere greater than 2 pi. Let's do it. Let's do it. Okay? So, arc length is equal to the integral from 0 to 2 pi of the square root of x prime of t, the opposite of sine, squared, y prime of t, cosine squared, z prime of t, 1 squared, dt. Ooh, look at this integral. It looks pretty nasty. Let's take a look. The integral from 0 to 2 pi. Well, what happens here inside there? You get a sine squared plus cosine squared is equal to 1 plus 1 is 2. Doesn't look so nasty anymore. So, square root of 2, take it out front. You have the integral from 0 to 2 pi of dt. The integral of dt is t, 0 to 2 pi. We end up with an answer of 2 square roots of 2 pi. So what we do have is an arc length that's a bit longer than 2 pi, by a factor of the square root of 2. Okay? 1.4 times as long. All right? Any questions on that? You'll certainly see something like that on the test. I don't know if I have you just set up the integral or actually do it. If I have you do the integral, it's going to come out something like this. Adrian?
No.
No. Bob? Bill? Go ahead. No. Okay. Any questions on that? All right, that's arc length. All right, it's just like parametric form. Let's do curvature. Okay. Curvature is usually denoted by kappa. Okay. Greek letter K. Curvature.
Water creatures?
Yes.
Yes. I think I remember something completely useless.
Wow. Okay.
Yet again.
Kappa, curvature, is equal to the magnitude of T prime over the magnitude of R prime. Okay? That's the definition of curvature, of a curve at any given point for T. Now, let's see if it makes some sense. Here. Let's check this out. Let's suppose we have some vector valued function that's going like this, R of t. What happens is t prime of t prime here, is telling us how fast the unit tangent vector is changing. Okay? If you move along this part of the curve, which is nearly linear, the unit tangent vector will hardly change at all. There's almost no change in the unit tangent vector. It's very close. Doesn't change very much. Certainly its length doesn't change because it's a unit vector. But what happens is, as you get near here, the vector changes a lot more. Changes direction a lot more, and the vector changes. Okay? So if we're going along in a straight line, that unit tangent vector is hardly changing. As you get to a point where the curve is curving more, there's greater change in that unit tangent vector. It goes from here to here to here, like this. If we take the magnitude of r prime, which is the speed of this particle, okay, if this is going slowly and the change is great, then we've got a curvature that's great, that's very big. If this is going very fast and this is changing at that same rate, the rate of change is slower, okay? So, the curvature is greatest where the curve is changing the fastest, the most, okay? Which makes some sense, all right? I think, right? Yeah. Where it's changing the greatest, the curvature is greatest. Where it's more linear-like, there's hardly any curvature at all, okay? There's one more thing I want to throw in here that's not really part of the test or anything like that, but I do want to point out we have what are called osculating circles, and on Monday I'll bring that in and show you. An osculating circle is a circle. Whoa, that's pretty much a perfect circle right there. Wow. Okay? All right? An osculating circle is one that's tangent to the curve. The radius of this osculating circle, say capital R, is the reciprocal of the curvature at that point. Okay? So, the radius, this is called the radius of curvature, by the way, the radius of curvature, the radius of that osculating circle, and I think I mentioned the word osculate. What does osculate mean?
That kind of thing. A kiss?
Kiss. That's what it means. Osculate means kiss. Okay? It's called a kissing circle. Okay? We can mention that here. Okay. All right? An osculating circle is a kissing circle. It's one that's tangent. The radius of that osculating circle, called the radius of curvature, is the reciprocal of the curvature.
Why is it called a kissing circle?
Because it's kissing the curve. It's touching it at exactly one point. It's tangent to it, okay? And that's the only reason. What's that?
Why is it just a tangent?
Well, it's a special tangent. See, you got an infinite number of tangent circles. Infinite number of tangent circles here. But there's only one osculating one whose radius is the reciprocal of the curvature, because it fits neatly, like right in here, where the curvature is the greatest. The osculating circle is the one that fits right in there. Okay? It fits in there perfectly. Yes, Nick?
Why is it so big then?
This one here, because the curvature of this curve at that point is very small. The more the curve looks like a line, the smaller its curvature, and the greater the radius of curvature, the greater the circle is, to fit right in there.
So there's a bunch of these circles everywhere, right?
No, for this point, there's only one.
No,
No, that's why I meant like the entire line. Like if you're.
Oh, yeah, you got it. Every point on this line has its own osculating circle. When you get down to here, you got this little tiny osculating circle. Why is it so tiny down there? Because the curvature of the curve is greatest there. That means the radius of curvature is the least. It's a little confusing, but you got to remember this. As the curve is curving more, the radius of curvature is less. The osculating circle is smaller. Yes?
Why did someone want to find this osculating circle?
Liam, I don't know.
I'm just trying to see like where it would be found. You know?
I tell you where it can be found. It can be found in my office, right right above the chess tables. All those pictures on there are Mathematica graphs that I drew, that I wrote, that are all osculating circles. They're osculating circles.
So
Yeah, I made all those. Of course they
Paint a
do.
picture
What's that?
of Mathematica.
What's that?
Okay. That's fine.
I'm going to bring it in on Monday. I'll show you the program that I wrote to generate these things.
Question.
Okay? Yes?
Now, what if the curvature is, say, like almost like a perfect circle?
Okay, this is what we're going to do right now. Let's suppose we have a curve that is a circle. Let's take a circle. Okay, let me ask you this. Let's suppose we have 3 circles. One whose radius is 1/2, one whose radius is 1, and one whose radius is 2. Which circle has the greatest curvature? The 1/2. The smaller circle has greater curvature. The radius of curvature of that circle of radius 1/2 is going to be equal to 2. Okay? The reciprocal. Okay? All right, we're going to do it out. We're going to do that out right now. Okay? The bigger circle is more linear. Its curvature is less. The circle of radius 2 is going to have curvature 1/2. Okay? All right. What's the curvature of a straight line?
0.
0. What's its radius of curvature? That's infinite. Yeah, that's infinite. What happens is, as you get this curve to look more and more linear-like, the osculating circle is increasing in size, gets bigger and bigger. Say down here, the osculating circle would be like this. And then as you head this way along the curve, the osculating circle down here is the smallest one. It fits right into that little piece right there. Okay? Let's do one. Let's do one. I'll tell you what, let's generalize this whole thing. Let's find the radius of curvature of a circle of radius r, capital R. Okay? And we'll find its curvature and its radius of curvature. You ready? Let's do it. All right, so here we go. First thing to do is define our circle of radius capital R, okay, as a vector valued function. Can someone come up with a vector valued function that will generate this circle of radius R?
R goes into R.
Thank you very much. That's exactly right. Okay. Thank you. Now, let's find the curvature, kappa, and we'll find the radius of curvature, the reciprocal of kappa, on this circle. So, well, here's what we got to do. We got to find R prime. R prime. What's that? You all set, Dylan? Yeah, okay. We're going to find the magnitude of r prime. We're going to have to use that as the denominator, the speed of this particle. Okay? Square root of r squared sine squared plus r squared cosine squared. Okay. Take out an r squared as an r, and you're left with the sine squared plus cosine squared in there, which is a 1. So the speed of this particle moving around the circle, okay, is r, the radius of that circle. Okay. Well, we've got to find the unit tangent vector. Let's find the tangent vector. Bless you. Unit tangent vector. Did somebody sneeze? Really? Wait, you sure? Oh, okay. All right. All right.
Never be too careful.
That's true. All right. T is equal to r prime over the magnitude of r prime. That's what a unit tangent vector is equal to. So we have r prime and the magnitude of r prime. Our unit tangent vector is opposite of sine, cosine. Okay? So let's take a point. Let's verify this. If we were to take some point here, let's say at pi over 4, say, our unit tangent vector at pi over 4 would be negative square root of 2 over 2, cosine pi square root of 2 over 2. It would go back this way and up. It would be like this. Okay? Okay, that would be our unit tangent vector.
Can you move it down?
Ooh, I'm off the chart there. Okay, something like that. Okay. And how would you find the principal unit normal vector here while I'm here? What would the principal unit normal vector be at this point? What do you do to find that?
What is it? Prime over magnitude?
Yeah, that's what it is, but I'm not going to do it out because we have that little trick. The little trick is to swap these guys
Make a negative.
and take the opposite or negative of one of them. Now, here is our principal unit normal vector. So which one do I want to take the opposite of? First one to make them both negative, or the second one to make them both positive?
Negative.
Make them both negative, that's correct. You want to take the opposite of the first to give you a vector pointing inward in the direction of motion. This would be your principal unit normal vector here, okay? That would be that. That's not part of the problem. I just threw that in there just for laughs. Okay. All right, what else do we have to do here? We have to continue on here. Tell you what, I've got some space up here. I'm going to go up here to get T prime. Okay. Here's T. T prime, take the derivative of this. Take the derivative. Okay. With me on that? And now let's take the magnitude of the derivative. Square that one, and we get that equal to 1. So, here we go. Kappa, the curvature of this circle of radius capital R is equal to the magnitude of T prime over the magnitude of R prime, definition of kappa. That's equal to magnitude of T prime, 1. That tells us what? The unit tangent vector is not changing at all, okay? It's the same one every time, okay? It's 1. And the magnitude of R prime is R. So kappa, the curvature of this circle, is 1 over R. With a unit circle, kappa is equal to 1. Okay? With a circle of radius 2, kappa is equal to 1/2. It's less. It's more linear-like. Okay? With a circle of radius 1/2, kappa is equal to 2. It has more curvature. It's changing faster. What is the radius of curvature of this circle? Radius of curvature. All right, I'm stuffing this in here, I guess. Radius of curvature. This is probably poor. Is the reciprocal of kappa. And what's the reciprocal of kappa? R. Well, that's kind of interesting. What does it mean? It means the osculating circle of this circle of radius R is what? There's one word that will describe what it's equal to. The osculating circle of this circle of radius capital R is, it is a circle, but you can be more specific. Is what? Say it again?
2 pi.
Well, the circumference, no, the circumference will be 2 pi R. So that's not it. Is what?
The curvature.
It's a reciprocal of curvature is equal to R, which is the question is, I guess, too nebulous.
The same circle?
Yes, it's itself. That's the word I was looking for. Is itself.
Yeah, I thought someone.
Wait, did you say that?
That's like the second thing someone said.
Yeah. Oh, I'm sorry. All right, itself. Was that you, Jimmy?
Yeah.
No. So the oscillating circle.
Yeah, you
of
just
a
pulled the
circle-
top of your
Yeah.
Mr. Burns.
Oh, is that what he does?
Yeah.
Oh.
Yeah.
I have a reason. I can't even hear. I mean, my hearing is really down the tube.
Maybe you just can't hear.
Maybe that's it. Could be. Maybe. All right. But anyhow, is itself. So it's a self-kissing circle. All right.
Wow.
The circle.
The lovely
Poor guy.
Just saying. That's what it is.
Question.
Yeah. Question. Go ahead.
At what point? You said at 1 point.
Every point on this circle, its osculating circle is itself. That's what it would be.
Is this going to be on the exam?
Osculating circles are not, but radius of curvature is. And curvature is. Now, radius of curvature, I don't know if I have that. I have to check the exam. But I do know I have a question on curvature, kappa. Now, I don't know if I have you actually doing out, but to find kappa is kind of a pain in the neck. Even with that parabola we did the other day, or an ellipse, it's kind of complicated. So on the test, I know in WebAssign, I'm pretty sure the only curvature problems you have are linear functions. And you know the answer to that is what? What's the curvature of a linear function?
0.
0. The curvature is 0. Radius of curvature is infinite. I know it gets confusing. The curvature is equal to 0. I'm pretty sure that's what you have on WebAssign. On the test, you either will have a circle or a line or something like that, because otherwise it's just too complicated to figure out. Either that or have you just set up the unit.
What about the projectile motion?
There will be a projectile motion on the test, that's for sure. Okay, that's a given. I will give you initial velocity, v sub naught. I'll give you an angle theta, and I'll give you a height h. And I'm going to ask for things like range, time in flight, range, max height, those kinds of things. I'm going to ask for those things.
So
Yes.
if we use our physics formulas.
You can use whatever you want. I think the physics formulas are, they'll work, but they're weird though. To me, they just, the ones we developed in calculus derived make more sense, in my opinion. Okay? That's my opinion. You can use whatever you want. You can use your physics formula as long as you know them and don't have to refer to notes or anything like that. Yeah. Yeah, you can, certainly. Because I'm not going to check your work. If your answer is right, fine. I'll tell you this, though, if you get it wrong, and I look at your work and you got these physics formulas down there, not only will I not give you partial credit, I will take off additional. All right. Any other questions?
I'll just draw some.
Well, that finishes the chapter. Monday, I'm gonna show you some osculating circle stuff, and I'll take any questions. I'll tell you what's on the test, and Tuesday we'll go over the lab, and Wednesday we'll take the questions, and then Thursday we'll take.
False pitch in for like real pizza.
Oh, Monday we got pizza coming in. Math team. Math team, we have an official date. Is
Oh God.
November 2nd, I think. There's an official. There's a Monday in there somewhere. I don't know. I think it's November 2nd.
I don't think I'm ready, Burns.
Yeah, I don't know if I'm ready.
I'm nervous. I think we need to start just math team all the time. Like, I will have to take a break from this class.
Maybe. All right, so we got to change of plans. And Monday, we've got the osculating circles math team problem
Math
in
teams
class.
all day.
All right. No.
You send that memo to Toby?
Wait, when's the exam specific?
The exam is Thursday.
So what are we doing Monday, Tuesday?
What's that?
We're doing Monday, Tuesday?
Monday, I'm going to show you some osculating circles and curvature by Mathematica. Tuesday, I'm going to show you the lab. And Wednesday for questions.
When are we going to start double?
When we start what?
Double.
Pretty soon, they're coming out. Next chapter is on multiple integral. Yeah, next chapter. Wait. Functions of two variables. No, actually, we do gradients next chapter, directional derivatives, and then we do multiple integrals chapter.
Toby is just doing stuff with him, and it doesn't really make sense. And he doesn't explain it. He doesn't explain it because it's math, and he just wants to teach physics.
Burns is pretty much shitting all over me. He's saying in the calc class, he's like, oh, you haven't learned this yet? Like, looks down for not knowing.
There's a couple words.
This is
recording.
It's still recording. We'll edit that.